welcome to my lab. Are you ready to learn? Yeah! Are you ready to have some fun? Yeah! Well, let's get started then. In my lab, whenever we do experiments, we obey all the safety rules. I want everyone to notice that I have my goggles on, and I also want you to see that we have a fire extinguisher ready to be used just in case something goes out of control. We're not planning on anything going out of control, but we have it as a safety precaution, and it is really ready to be used, just like that. I'm going to put it right here where you and I know where it is in case it is needed. Now, when you burn something that has carbon in it, as I'm doing right now, I'm burning some propane gas or the wax that's burning in this candle here, we form carbon dioxide. Carbon dioxide, among other things. Carbon dioxide is a gas at room temperature. It has no color, so we can't see it. It has no smell, we can't smell it. And I'm going to do some experiments with a different form of carbon dioxide than the gaseous form. This form, let me turn this off here so that, okay, then I'm going to use solid carbon dioxide, something we call dry ice. And you notice I'm putting what on? That's because I want to protect my hands from this very cold substance that we call dry ice. Here are some chunks of dry ice. Dry ice is solid carbon dioxide. Its temperature is minus 78 degrees Celsius. It's really, really very cold. If I touch it with my bare skin, I will get a severe frostbite, and I don't want that to happen. And you don't want me to have that accident either, right? That's why I use these gloves to protect my hands from this cold substance, dry ice. Dry ice changes from being a solid to a gas directly without melting. We call that process sublimation. Can you say sublimation? Sublimation. Sublimation is happening right now, but we can't see it. Why can't we see it? Because carbon dioxide gas is colorless, and it's also odorless. It has no smell. I'm going to take chunks of dry ice and put them in this conical flask. We call it an Erlenmeyer flask. And this dry ice will sublime inside the flask and outside the flask. But I want to fill the flask with as much carbon dioxide as I can in this short period of time. And what you see there is a little mist, right? That's the condensed water vapor. There was a little moisture inside the flask. So there it is. And I now will move over and light the candles that we have over here. You help me out. How many candles do we have? 1, 2, 3, 4, 5, 6. All right, 6 lit candles. And what I'm going to do now is take the flask, the Erlenmeyer flask, with the dry ice at the bottom that is undergoing sublimation, and I'm going to lift it up. I'm going to pour the carbon dioxide gas out of the flask. Our carbon dioxide is denser than air. It flowed down. Now I will go back to this side and light the lowest candle on the steps, and then use another gas that is denser than air. This gas is propane. It's in this propane bottle right here. It's connected to a funnel and some Tygon tubing to the valve of the propane tank. So what I'm going to do is fill this beaker with propane gas. Propane is colorless, so we can't see it. So I'm going to do this by opening the valve, and you'll hear the sound of the gas flowing. Here we go. You hear it? And now watch what will happen when I take this beaker full of propane gas and pour the propane gas down the Do you like this experiment? Yeah. Shall I do it again? Yeah. All right, I'll do it again. We'll put this candle out. I was trying to light up all the candles, but I succeeded in lighting up one. And we want to make sure everything is out of here, right? Including the carbon dioxide gas that formed, right? So it's all coming out. And then I go back and fill the beaker with propane gas. Here we go. And let's try this one in the dark. This experiment I'm going to do with a carbonated beverage. Do you know why we call them carbonated beverages? Because they have in them carbon dioxide. And they have a lot of carbon dioxide. For this experiment, I'm going to use a baby bottle. Remember baby bottles? Yes, yes. This baby bottle has been slightly modified. I have replaced the nipple that has the hole in it. I've replaced it with the rubber bulb from a medicine dropper. I would like to show you how strong this piece of rubber is by blowing air into it to see if I can inflate it. Here we go. I can't do it. It's a very, very strong piece of rubber. So now I want you to listen to this very familiar sound as I open the can. You heard that? That's because the liquid that is full of carbonation now is open to the atmosphere. I'm going to take the baby bottle and fill it up with the drink. And what do you see? Do you see bubbles? Yes. You see fizz, right? What kind of bubbles are those? Carbon dioxide bubbles. Where are they coming from? They're coming from the drink that's inside the can. The canning company, the bottling company, spend a lot of money compressing the carbon dioxide to make it dissolve in the liquid so we get to enjoy the carbonated beverage. Now, I'm going to put the screw cap on, and I'm going to tighten it. What should I do next? Shake it. You've done this experiment before, huh? So, okay, I'm going to shake it like this, and now you see how much carbonation is in that drink. The pressure of carbon dioxide is able to inflate this strong piece of rubber that neither I nor any other human being can inflate with all the powers of our lungs. So, of course you know about carbonated beverages and what they do when you sip them. What happens when you take a sip or two of a carbonated beverage? What do? You burp, yes. When you burp, would you please do it gently and politely? You burp because the carbon dioxide gas is coming out of the liquid, just like I did here when I shook it up. So let's see if I can release the pressure here very gently and very carefully. If I do it fast, I'll make a mess. I know some of you would like me to make a mess, but hey, it's dripping a little bit. There it is. It's been released. It's open to the atmosphere. And when the gas bubbles will continue to come out, and eventually what we end up with is what we call a flat drink. The drink goes flat. Why does it go flat? Because there's no more carbonation in it, right? And it doesn't taste as good. Well, why do we like carbonated beverages? We like them because when we put the liquid in our mouth, the tiny gas bubbles come out of the liquid and tingle us under the tongue and give us a very pleasant sensation. So I wanted to share that with you, more about experiments that you can do In fact, you can do this one at home if you want to. We have it on the Science is Fun website. All you have to do is go to www.scifun.org, scifun.org. You'll find this experiment and many other experiments that you can download, enjoy, and do it with all members of the family and with your friends. Now, I want to do another experiment. This experiment I want to do with this candle. I want to reach into my back pocket, and I want to pull my wallet out. What do people usually keep in their wallets? Money. What else? Credit cards, pictures, what else? Driver's license if you're old enough to have one, right? So I want you to pay close attention, as you've been doing. Pay close attention to these experiments because I don't want anyone to miss out on anything that's really exciting. So here we go. I take one $20 bill out of my wallet and I put it in the flame just like that, and disappears into thin air. Did you see that? I wish I had a camera to get the expression on your face over there. You know that was not a real $20 bill. That was a fake dollar bill, a $20 bill. That was a phony $20 bill. It's called flash paper. What do we always do in science? Repeat the experiment. So I take what looks like a $20 bill, but it isn't. All right? And now you pay close attention as I bring it close to the flame here and see what happens. Didn't even touch the flame. You saw that, right? Right? So did you like that experiment? Good, good. All right. Thank you. All right, so now what I'm going to do is reach into my wallet and get out a real $20 bill, okay? There's nothing phony about this. Yes, oh, wow, she said, I heard that. I saw you say that. Okay, $20. You know what I'm going to do with it, right? The same experiment. I'll do the same experiment, but I want you to see that I have a jar here, and I have a liquid in this jar. What do you suppose this liquid is? Well, what does it look like? What does it look like? It looks like water. You know from experience what water looks like. So what I'm going to do is take the $20 bill. I'm going to soak it in this clear and colorless liquid. That's how we really describe this. Water is a clear and colorless liquid. And I'm going to try to fish it out. Try to fish it out. Here, make sure it's soaked well. Fish it out. You see it's dripping like any wet object would. Now, you ready for this? Take a close look at the $20 bill. It may be the last time you see it in this form right here. And I put it in the flame. And there is a $20 bill on fire, or is it? You saw the flame, didn't you? But the $20 is intact. So now I ask you, can this liquid be water? No. You know from experience that water doesn't burn under these conditions. I'll tell you what this liquid is. It's a mixture of water and something we call rubbing alcohol, isopropyl alcohol. Half and half, 50%. We also added a little bit of table salt to it so that we can see the color of the flame better. The yellow color that we saw was because of the table salt that's in there. Otherwise, as you know from experience, the color of the alcohol flame is bluish. Well, this is a good $20 bill. It's a little bit wet, but I'm going to put it back in my wallet because I'm going to put it to good use later on. So I put this one back here, put my wallet back in place. Did you like that experiment? Yeah. Thank you. And now I'm going to do an experiment using a very cold liquid called liquid nitrogen. Liquid nitrogen is at minus 196 degrees Celsius. It's really, really cold. And we keep it in a thermos bottle. This thermos bottle is called a Duar flask. And I pour some out. And you can see this is a good way to dust off the tabletop. And what I want to do is show you the effect of cold temperature using this dish right here. I'm going to show you the effect of cold temperature on this balloon. So I take the balloon and I put it inside the dish. I have to hold it down because this balloon has in it helium. And I hold it down like this, and I add the liquid nitrogen. I keep it away from my skin. And look at the balloon collapse. It collapses because the helium atoms inside the balloon have been slowed down in their movement when cooled with the liquid nitrogen. When the nitrogen evaporates, then the balloon warms up and goes up in the air. I really like to do experiments with balloons, and I'm going to now reach into my pocket and get out a balloon. And I'm going to inflate the balloon. That's about big enough. Maybe I'll let some air out. And then I will tie it. And I want to ask you a question. Is there a way for me to hold this balloon up in the air without touching it? Is there? I don't mean put it on a beaker like this. I'm not touching. I mean, is there a way for me or for you to suspend this balloon up in the air without touching it? Yes or no? Yes. Those of you who are saying yes, you already know how it's done, or maybe you have confidence in me. Otherwise, I would not ask that question, right? And so let's try it and see what happens. I take the balloon and let go of it, it drops down. You know that, right? But if I try to blow on it like so, kind of held it up in the air without touching it, but that's hard on my neck. So suppose I use, what's this? Suppose I do this. Is the balloon up in the air? Am I touching it? What's holding the balloon up in the air? Air. There's air right now. It drops back down. What's coming out of the nozzle? No, it's not on hot, it's on cold. Okay? What's coming out of the nozzle is a stream of moving air. You know that, right? So let's see if I can get this higher. You think you can do this at home? Yeah. When you try it at home, try to tilt the hairdryer and see what kind of angle you can get away with before the balloon falls down. I'll turn it off this way. And let's see what else I have here. I have a couple of other items here. I have, what is this? And this is a styrofoam ball. Ta-da! You think you can do this at home? You try it and have as much fun as I'm having right now doing it with you and for you. All right, so that's more experiments with levitation of the balloon related to a very important scientific principle called Bernoulli's principle. Now I'd like to do an experiment with small plastic bottles. Here's one. Here's another one. Here's a bigger one, and an even bigger one. I'd like to tell you about these bottles because what they have in them are screws that are inserted, but they're not touching on the outside, on the inside. They're separated by a distance about half a centimeter. They're not touching at all. And there's a cork on top of each one, and there's also a clear and colorless liquid at the bottom of each of these 4 bottles. So what I'm going to do is use what is called a Tesla coil, which is a way by which we can generate a spark. If I push the button, there's a spark coming off here, but I want to show you this spark by taking this metallic object and hanging onto it real tight as we turn the lights down, and you'll see how the spark now jumps across. You see it? All right. All right, now with the lights back up, please. What I'm going to do is touch one of the screws in each of the bottles and see if I can make the spark jump across the gap that separates the two screws, and we'll see what happens. You ready? Here we go. Let's try this one. What we're doing here, we're setting off an explosion. That's because the liquid at the bottom is actually an alcohol, and the vapor of the alcohol gets ignited when the spark jumps across the gap that separates the two screws. Ooh. How about we try this one in the dark? Should we try this one in the dark? Let's see what happens. You ready? You sure you're ready for this one? All right, here we go. Yes, safety comes first, right? So we obey the safety rules. At this time, I would like you to welcome our chemistry lecture demonstrator, Mr. Jim Maynard. Jim? Hi, Jim.
Hi.
What do you have for us?
I have a demo for you that involves this syringe and this small Erlenmeyer flask with a clear and colorless substance in. And I actually have one more thing I need. Okay, so this is my demo.
This looks like a long glass tube.
Yes, it is. It's a long glass tube, and you can notice it's stoppered on both ends. And inside is a clear and colorless gas. It's actually nitrous oxide, also called laughing gas.
Laughing gas. All right.
Okay. We're going to do an experiment with the laughing gas. We're going to combine it with this clear and colorless liquid, which is actually called carbon disulfide. It's a foul-smelling liquid like most sulfides, and it has a structure like carbon dioxide. We're going to take this liquid, we're going to put it in here, we're going to mix them together, and we're going to do a combustion reaction. So in order to do this, though, I need to get up on the table. And I need my syringe. So I'm going to take and withdraw some of this carbon disulfide with the syringe so I don't have to smell it, and because it isn't really good for you. But don't worry, it doesn't hurt a bit. All right. So I'm withdrawing a certain amount of fluid from here, and I'm going to introduce it to this large glass tube. Okay. And in it goes. And I'm going to mix it in a rather special way as well. So, let's take it off here. Okay. 1, 2, 2.5. Okay, I think we're sufficiently mixed. Now, what I'm going to do is light this. So, Bassam, if you could help me find a torch.
Oh, yeah. Here it is.
And with the lights down, please. 1, 2, 3. Thank you.
Wow. Now, what's this yellow stuff on the inside of the tube?
Yeah, this yellow stuff on the inside of the tube is sulfur. So this reaction starts out with the carbon disulfide and the nitrous oxide, and you get nitrogen, carbon dioxide, and sulfur. I like this demo for 2 reasons. 1, it's very spectacular. And 2, Le Chatelier himself, of Le Chatelier's principle, used to do this very demo in front of his students over a century ago. Thank you very much.
Fabulous. Thank you very much. Thank you. Here is a green liquid. Here's an orange liquid. And I have a blue liquid. And I also have a small beaker with a little bit of a yellowish, lightly yellowish liquid. And what I'm going to do is we now express to you my thanks and all the thanks from the people in my lab for your being such a wonderful audience. Here's our grand finale for you. Here's one. And here's another one. And here is the third one. Thank you all very much. Thank you. Thank you.